For those of you that do not want to use Mathematica, I'm showing you how to do a numerical integration. Basically what you need to do is to get the function, the acceleration, as a function of position S. So what I've done is I've in this cell C1, I put in a number that I want the change in S to go, and so over here I load up S's from the initial value that I have, and then it just increases by the amount in C1 until I get to the number 2. So you can see the formula that I'm using. So here I'm adding 0.02 to 1, and then I'm adding another 0.02, and that proceeds all the way down until you get to 2. And then the acceleration has this formula, which I type in, and then I'm going to copy that from here down till I get to 2. So I've copied that in. Alright, so now I have A versus S. If you want to see what that looks like, you can create a graph. I'll pause that, and then I'll just insert a graph so you can see what it looks like. Okay, so basically this is what it looks like, the A versus S from S1 to 2. And essentially then what you want to do is find the area under this curve. So what I'm going to do is I'm going to treat the area as little rectangles, and so I'm going to do a rectangular, the size of a rectangle for each one of these points along here. So I'm going to pause till I get that set up. Okay, so in this formula right here, what I've done is I've taken the the height of a rectangle, 1.25, and I've multiplied by the width, which is 0.02. So this number in D2 is going to represent the little piece of area underneath the A curve for the first 0.02 value of S, right? So that's what that is, so which is 0.05. Now I'm going to copy that down to all of the cells. Okay, so this is the individual rectangles under that cell, and you can see that they're all pretty much the same. But you saw a plot of it before, and yeah, you know, it didn't change that much. So anyway, this is the area. Make note of the notation. The dollar sign here says that when you copy it, leave the 1 alone. So you see right here, it's always C1, C1, C1. So that's Excel. Hopefully you've been taught to use Excel. Then the total area is simply the sum of all of these areas, right? So all I'm going to do is I'm going to add up these areas, and that'll be the total integral. All right, so the total integral is 0.852, and that's going to equal v squared 1/2. This should equal 0.5 times v squared. Okay, I'm going to pull out my I'm going to pause while I do this calculation. Okay, I'm back. So anyway, the integral is 0.852. So here what I'm going to do is, it's probably easier to do this calculation by hand. So if you take the integral, multiply, I'm trying to solve for v, right? So if you take the integral, that one, you multiply by 2, you get 1.7. That's equal to v squared. So I want to take the square root of that, number, and it's 1.306. From Mathematica, I think the answer was about 1.29, so it's not too bad. Mathematica is obviously more accurate because it's not doing a numerical integration, it's doing the actual integration. So you're getting pretty close to the same thing. The way that you can make it more accurate would be to change this number right here, the size of the rectangles. The smaller the rectangle, the more accurate the integral will be. And there's other ways of doing numerical integration that are even better. You'll learn about these in engineering analysis too. That's it.